class of solids called quasicrystals. Okay. So, before we go into how these quasicrystals have come up and to understand what these quasicrystals are, let us have a look at how the whole field has evolved. If you look at physical metallurgy and look at a few milestones in physical metallurgy, particularly looking at the microscopy of it and the crystal structure and the microstructure of various materials, it all started with I would say around 1863, when Sorby has talked about the perlite. Because you all know that for a metallurgist the most important thing is the steel, and the strength in the steel basically comes from the perlite. So, the understanding of the microstructure of perlite was very crucial those days to understand the mechanical properties of steels. So, this was the starting point of physical metallurgy, one can say. Then 1998 people talked about the iron carbon diagram. That was the first time when iron carbon Austin, with his name we now call the phase austenite. Okay. So, this is the person Robert Austin, and then we had the Hume-Rothery rules which came in 1926, and a new type of electron compounds which are called Hume-Rothery compounds have been discovered those days. And then till 1934 people did not really see dislocations, though people talked about the presence of some defects which are probably giving you the slip. But the first discovery of dislocations or observation of dislocations in a transmission electron microscope came from Taylor and Oravan and this Oravan is a person whom you might have heard about, the Oravan bowing, we say around particles. When a dislocations are pushed, they bend around a particle, which is called Oravan bowing. And then one had to wait till 1960 for metastable phases to come into picture. Though we know about a few metastable phases such as the cementite, but processing of materials under highly non-equilibrium conditions was not known till 1960, when Paul Dewey has at Caltech has developed a new technique called rapid solidification processing, and you all know about rapid solidification processing by now. And then it was in 81 the nanocrystals have come into picture. The Gleiter in Germany, we talked about it before, and it is at 84 Shetman has seen a new type of diffraction pattern. We will talk about it a little later in greater detail, and that is what is the birth of a new class of solids called quasicrystals. So, that is 1984, Dan Schertman will say. And then last few classes we have been talking about the bulk metallic glasses. That was 1988, Inoue, Professor Inoue at Japan, the Institute of Materials Research, Tohoku University. He was a key person, and another gentleman in US, Bill Johnson, people call him Bill Johnson, and he is another man who has been working a lot on this. So, these are kind of milestones in this field of I would say non-equilibrium processes and the field of metastable materials. And if you look at how this whole thing evolved, everything started with these three very crucial phase diagrams: the copper gold, gold silver, and the copper silver. I told you before that Paul Dewey started this field with this particular three phase diagrams in mind. He thought the copper, silver, gold, if you look at the atomic radii, copper is about 0.128 nanometers, silver and gold more or less the same, 0.144, that means about 1.44 angstroms, and valency all of them have the same, electronegativity 1.9 for both copper and silver, whereas the gold it's about 2.4. So, if you carefully look at these three, they are all very close to each other with a small changes definitely. But when you look at the phase diagram, the copper gold is an isomorphous phase diagram, the gold silver is again another isomorphous phase diagram, whereas the copper silver is a eutectic. The one possibility that one can attribute this to atomic size difference, but this atomic size difference is not too large. If one looks at the differences in terms of percentage is not too large. So, many people did, and if you look at electronegativity, they are the same. So, there was for quite some time people did not understand this very well. Even now the theory of why copper silver has to give eutectic is not really clear, but one knows that if he can take the liquid and cool it rapidly, now one can suppress that eutectic formation and can get the isomorphous solid solution from one end of the copper to the other end, which is the silver. So throughout single phase field can be achieved in a copper silver. And the other diagrams which Paul Dubé looked at those days are all the eutectic phase diagrams. So he took silver copper, this was the starting point, and then he went into silver germanium and took again the eutectic composition and tried to cool them rapidly. He did not get a solid solution here, but he got a metastable crystal structure, a crystal structure which did not exist in the phase diagram, a phase which is called the gamma phase, which did not exist, and when they tried to index that, it is not this terminal solid solution, either it is not a silver terminal solid solution, it is not a germanium terminal solid solution. So it is a phase which does not exist into this. So this is what are called metastable phases, which sometimes form under fast cooling conditions which do not exist in the phase diagrams. So it is possible that they exist as clusters in the liquid, and when the liquid is cooled rapidly, instead of the equilibrium phase coming out of the liquid, so the non-equilibrium phase which can come out, because the activation barrier for that non-equilibrium phase may be very small. For example, as we see in case of edge hardening, we know that Al to Cu does not come out, but the Gp Jones, theta double prime, theta prime, all these phases come out. Similarly, you also might know that when I take a steel, quench it from high temperature, from the austenite, what do I get? Martensite. When we start heating this martensite for what is called tempering, you don't get the cementite directly. You go through another stage called epsilon carbide, okay, which people call it Fe2.2C, whose crystal structure is hexagonal, which is close to that of the either the FCC structure, which is the original structure from which the martensite is obtained. So as a result, one can easily say that the formation of HCP will have a lower activation barrier than the formation of the orthorhombic the Fe3C, which is the cementite. So like that, we know in a number of solid state reactions, such second phases which do not exist in the phase diagrams can form, and similarly when somebody cools from the liquid to solid also, it is possible that some metastable phases can form. And then he took this gold silicon, which is again a eutectic, and if you compare the gold silver copper with gold silicon, you can clearly see that this is a deeper eutectic than this. Just by looking at it, one can know. You look at the two pure metal melting points and look at the eutectic temperature, compare with the two pure metal melting points in gold silicon and the eutectic, and you can see from here that the eutectic is much deeper than this. And when he took that particular composition, which is about 20% silicon, and what he got was a glass. So this was the kind of various metastable phases that Paul Dubé has obtained in just 1 year, starting from extension of solid solubility, then the metastable crystal structures and the metallic glasses. The only thing that had to wait for a long time is what is called the quasicrystal, which one had to wait till 1984, and unfortunately Paul Dubé did not look at it because this is nothing but a peritectic kind of phase diagram. So he was always looking at eutectics and trying to look at eutectics and see if in any eutectic can he extend the solid solubility, because rapid solidification, one of the most important thing is extension of solid solubility. When we talk in detail about RSP, we will discuss this, and what you can see is that whereas in this particular case, which is basically a peritectic diagram, what we usually call it as a cascade of peritectics, a number of peritectics. The classical example of such a cascade of peritectics is what system? A very common system, which copper zinc, yes, copper zinc is a cascade of peritectics, we say. So it has a number of peritectics. Aluminum titanium is another. So there are so many peritectics here, and one basic difference between metallic glass forming systems and quasicrystal forming systems is that you rarely get a metallic glass in a system which shows peritectics. You need eutectics, particularly deep eutectics, for a liquid to be stabilized for the glass to form. Whereas systems with peritectics, unless you go to really very high cooling rates, you will not be able to get the glass. So whereas the quasicrystals are obtained in those systems where you have a number of intermetallic compounds. Mostly quasicrystals are nothing but intermetallic compounds having certain stoichiometries, and that's why people call them as Hume-Rothery phases or what are called electron compounds. Many quasicrystals stick to some E by A ratio. There are a number of quasicrystals which have a fixed E by A ratios. We will talk about it a little later again in detail. So you can see that aluminum manganese was the first system, and this was obtained at about 14% manganese. We will talk about it later also in detail. And so this was the aluminum manganese phase diagram, where at 14% manganese you have a phase called Al6Mn. That is the phase which is called rational approximant for quasicrystal. What is the meaning of rational approximant? That means its crystal structure is very close to that of a quasicrystalline arrangement of atoms. So there are certain crystal structures which are available in various phase diagrams whose structure is to some extent correlated to the quasicrystalline structure, and in all those systems it is very easy to get quasicrystals. One such example is Al6Mn, another such example is in aluminum iron. Al3Fe is another phase which is very close to that of quasicrystalline composition. So if you take that composition, which is something like 25% iron and 75% aluminum, such a composition can easily give a quasicrystal. There are a number of such systems where people have obtained quasicrystals now. And how do we basically define this? Where do you put this quasicrystal between the crystal and amorphous? As you can see from here, the crystal is one which has both rotational and translational symmetry. We talked about it when we were talking about structure of materials. And what are the types of rotational symmetries that are possible? These are what are called the crystallographically allowed symmetries, the 2, 3, 4 and 6. I will not talk about one-fold symmetry, because one-fold symmetry is what is called a trivial symmetry. Every structure should have a one-fold symmetry. So we will not talk about one-fold symmetry, but the 2-fold, 3-fold, 4-fold and 6-fold symmetries are called the crystallographic symmetries. And if you go to amorphous, it does not have both rotational and translation symmetry. And when you look at quasicrystal, quasicrystal is that which has a forbidden rotational symmetry, which is an example is 5-fold. It can have a 8-fold symmetry, it can have a 10-fold symmetry, it can have 12-fold symmetry. There are a number of such symmetries which have been observed in a number of systems which do not fit with the rotational symmetry, the translational symmetry. Why is that so? If you look at any crystal structure with two atoms here, let us say an atom A, another atom B here, the distance between these two, if you consider it as x, try to rotate this B with respect to the A by certain angle theta, and similarly rotate A with respect to B by again the same angle theta. If you now rotate and try to now look at what is the distance between this new position, which is B dash, let us say, B has been rotated and brought here, A has been rotated and brought here, this is called A dash. These are the two new atomic positions, and if you look at this direction is parallel to this atomic direction, isn't it? Because these two directions are parallel, the distance between these two atomic positions, in principle, if it is a crystal, it should be integral multiples of x. If this is x, this should be n into x, where n can be either 0 or 1 or 2 or 3 if it is crystalline. Why? Because a crystal is that which has a three-dimensional periodic arrangement of atoms. That is how we define. And if there is a periodic arrangement of atoms, if there is an atomic direction like this AB direction, A dash B dash direction is parallel to AB direction, and because this is A dash B dash is parallel to AB direction, the distance between these two atoms should be integral multiples of this, and that is possible only when I take a 3-fold symmetry or 2-fold symmetry or 4-fold symmetry or 6-fold symmetry. For 2-fold symmetry the angle is 180 degrees, for 3-fold it is 120, for 4-fold it is 90 degrees, for 6-fold it is 60 degrees. If it is a 2-fold symmetry, I rotate it by 180 degrees, where does this B atom will come? It will come in the same line in this direction. If it is 120 degrees, you come to some point here. Similarly, if you take A, it will come somewhere here. Obviously, now the new distance, if you want to call it as x dash will be equal to 3 times x, 3x. So similarly, if I take 3-fold symmetry, then it is 120 degrees. If it is 120 degrees of rotation, then this B dash, A dash distance, if you look at it, what will be? It will be 2x. And if it is 90 degrees, then x dash will be equal to x. And if it is 60 degrees, x dash will be equal to 0, which is 0 into x, let us say n equal to 0. So n can be 0, 1, 2 or 3 depending on what is the symmetry. But if the symmetry is 5-fold, if you rotate this B atom with respect to A atom by an angle which is something like how much? Okay, either 72 or 108 degrees, depending on the internal angle or the external angle for a 5-fold symmetry. So if you take a pentagon, what is the internal angle? Internal angle is always 108 degrees. So if I rotate it by 108 degrees, and you can try to calculate what is the distance, you will see that distance will never be integral multiples of x. So that means a 5-fold symmetry is not compatible with the translational symmetry, and hence those days when the crystallography was developed for crystals, people have never considered a 5-fold symmetry to be a part of allowed rotational symmetries. That is why people call it as forbidden symmetry. It is not possible, but you will see slowly that people have observed such symmetries in a number of solids. For example, if you look at platonic solids, which we talked about it in the first few classes, you can see 2 of these platonic solids have a 5-fold symmetry. Okay, you look at the dodecahedron, you look at the icosahedron, both of them have 5-fold symmetries. So out of the 5 regular solids, as I told you, there are no more regular solids. The maximum number of regular solids possible is only 5. We have proved this in our class. And so out of these 5, 40%, okay, 2 of them have 5-fold symmetry. But unfortunately, the people, though this was developed by Plato in even before AD started, in around 500 BC, but till recently, till 1984, people were unable to see any crystals, any solid materials having that kind of symmetries. Okay, and it was only recently people have talked about it. But when people have developed these quasicrystals and started looking at many of the crystal structures, they started seeing, yes, many of these crystals have such symmetries. One such example is aluminum zinc magnesium compound. This is a compound which has 3-layered kind of a structure. You have an internal layer which is an aluminum with 12 atoms, which is nothing but an icosahedron. How many corners are there in an icosahedron? Icosahedron has how many corners? It will be 12. Corners. Imagine a pentagon, another pentagon, rotated with respect to each other, and two vertices, one on top, one on bottom. In fact, I brought icosahedron some time back and showed you. So that's, you go back, you look at this icosahedron, that is E. What you have is a pentagon, one, you can see one corner, another corner, another corner, another corner, and one behind, 5 corners there, another 5 corners here, and one on top, one at the bottom. So total you have 12 corners. At these 12 corners you will have 12 aluminum atoms which form the inside layer of this the particular cluster, which is called Bergman cluster, aluminum zinc magnesium cluster. And then you have a next layer which is consisting of zinc and magnesium with 20 such atoms, which is called a dodecahedron. Dodecahedron has 20 corners. You can look at this. This is a dodecahedron. It will have 20 corners if you look at it. You look at any of the pentagon, so you have 5 corners there, and the next layer will be 10 corners surrounding this, and again at the bottom you have another 5 another pentagon. So you have a pentagon, another pentagon at the bottom, and then 10 corners coming at the center of that. So that is a 20 cornered dodecahedron. And then you have another what is called icosahedron, which with about 60 atoms. So you can imagine how many total number of atoms are there in this. It's about 92 atoms in this cluster, and the number of such clusters, there are also certain compounds which have more than about 1000 atoms in the unit cell, and there are such complicated crystal structures existing. But those days people did not really look very closely into these complicated structures. They said these are complicated, just left it. But then when the quasicrystals have been discovered, people started looking at them in a closer look, and then started realizing, yes, there is an icosahedral symmetry in many of these such clusters. And so this is another way of arranging Bergman clusters. You take a cubic crystal, put at one corner an icosahedron like what you see for the aluminum in the previous Bergman cluster, and then the next layer like a zinc magnesium layer, then another next layer of aluminum. Like that, if you put it in one cluster in one corner containing about 92 atoms, and put such 92 atom clusters at each of the body corners, you can imagine you are now developing a cubic structure with this kind of clusters at each corner, and which is basically a cubic structure. But as I told you before, whenever we define a unit cell, that's why we do not talk in terms of what are the number of atoms per unit cell. We always talk of number of lattice points per unit cell, because at each lattice point you can put 1000 atoms or 1 atom. It depends on the type of material. So in this particular material, which is the aluminum zinc magnesium compound, you will have 92 atoms at each body corner. So you can have such crystal structures, and all of them have some icosahedral symmetry. And this is another type of clusters which are called McKay clusters. Again, here also you will always find a icosahedral symmetry. It's slightly different from the Bergman type of clusters, but all these have large number of atoms in them. And all of them, the common thread in among all these clusters is that they all have icosahedral symmetry. And when people looked at such materials in a electron microscope, this is what they saw. The first time in 1984, when Dan Shetman looked at aluminum 86 manganese 14 alloy, what he saw was this type of a diffraction pattern. If you carefully look at this diffraction pattern, there is a central spot. What is that central spot? It's a transmitted beam in electron diffraction. And look at the spots which are surrounding that. You can see, if you carefully start from one corner and do not forget where you have started with, and then count the total number of spots around that central spot, you will see there are 10 spots. And you have another concentric circle, another 10 spots, and you go to another circle, you will have another 10 spots, and like that you will have, and each of them will have 10 spots, suggesting that it is a 10-fold symmetry. In fact, this is another important point that you should know, that if you look at any material having a 5-fold symmetry and look at it in an electron diffraction pattern, it does not look like a 5-fold symmetry, it will always look like a 10-fold symmetry. Why is this so? For example, I take a cube. What is the typical symmetry of a cube? Cubic crystal? It has a 4 3/4, okay, and 3 4/4. So if I take an axis which is perpendicular to the 111 plane, that means if I send the electron beam such that it is going perpendicular to the 111 plane of a cubic crystal which has been kept in the path of the electron beam. Let us say I have put a sample in a TEM and then oriented my sample in such a way that the 111 plane is now perpendicular to the electron beam. Now when the electron beam is coming through the sample, it comes across the 111 plane and then tries to see what is the symmetry of atoms around that plane, and the diffracted beam that you get, look at the diffracted beams, and what you see is you will see a transmitted spot like that and a diffraction spots which look like this, and so on. This is the first layer and there will be many order. This is called first order reflection, second order reflection will be there, third order reflection will be there. Okay. For example, in Bragg's law we talk of lambda equal to 2d sin theta. So there we talk about n lambda equal to 2d sin theta, which is n is the order of reflection. Okay. So similarly here, if we take the first order reflection, this is what you see, but it has a 3-fold symmetry. The cube has a 3-fold symmetry, but when you look at this, what you see is you don't see a 3-fold symmetry, but you see a 6-fold symmetry, and cube does not have a 6-fold symmetry. Why is that? The reason is simple. Reason is, if you look at the diffraction, the intensity of the diffracted spot, if this is a diffracted spot, the intensity I of any HKL plane is equal to what? Is equal to the square of the structure factor. Yes? Anyone who has gone through X-ray diffraction, they all know this. So intensity is square of the structure factor. Now if I look at the structure factor of an HKL plane and compare with the structure factor of H bar, K bar, L bar plane, two planes which are parallel to each other, the structure factor of this is always nothing but the negative of the other structure factor. They are the same in magnitude, but difference in the sign only. And if I look at this kind of situation and take the square of this structure factor, the intensity of the HKL plane will always be equal to intensity of H bar, K bar, L bar. So if I have a 3-fold symmetry in a crystal, for example, if this is one spot, then this is the other spot and this is the other spot corresponding to the 3-fold symmetry, then if this is what I call the HKL plane, some HKL plane, the H bar, K bar, L bar will always be here, isn't it? It will have an inversion symmetry. Okay. So H bar, K bar, L bar will be 180 degrees opposite to the HKL plane. If the HKL spot is here, the H bar, K bar, L bar will be below. And so the intensity of this H bar, K bar, L bar will also be equal to that of the intensity of the HKL. So because of which, the moment there is a spot here, you will get another spot here with the same intensity. Same thing is true with the other 3 spots, and because of which it looks like a 6-fold symmetry, but you will not know whether it is a 3-fold symmetry or 6-fold symmetry. In fact, this is one of the problems in finding out. If you put an unknown crystal into a TEM,
if it would have been 6-fold symmetry, then we would have seen 12 spots.
No, a 6-fold symmetry will always give you 6-fold because it will be overlapping there. So as a result, if you look at a cubic crystal in TEM or a pinhole X-ray diffraction, whether it is pinhole X-ray diffraction or TEM, they are basically similar, that you get what is called the diffraction spots instead of diffraction peaks. So if you look at the, you put a crystal inside a TEM and then pass the electron beam, you get this kind of a 6-fold diffraction pattern. Immediately one thing is clear to you from this, that the crystal that you are looking at is any of the 3 possible crystal structures. What are the 3 possible crystal structures which can give you this kind of a diffraction pattern? Another is? Yes, there is one more possibility. Rhombohedron. Be confident. Okay. So it's cubic, hexagonal and rhombohedron. All these 3 have a 3-fold symmetry in them. There is no other crystal which has a 3-fold symmetry. So from this, from the elimination technique, I can say this particular crystal I am looking at cannot be tetragonal, cannot be orthorhombic, and it cannot be either monoclinic or triclinic. So it has to be one of these 3. And if it is one of these 3, what is it? How do I find out? That is when in a TEM we have the facility of what is called tilting the sample. I can keep the beam, I cannot tilt the beam unfortunately, because the source for the beam is fixed. What is the source for the electron beam? It is a filament, tungsten filament, which is heated, and tungsten filament is kept at the top and that is fixed. So you cannot move the tungsten filament. So, but what you can do is you can tilt your sample. When I tilt my sample, I can change the sample, the orientation of the sample from the 1-1-1 orientation to some other orientation. And if I change this orientation, if I get a 4-fold kind of symmetry, that means a symmetry which looks like this. With a central transmitted spot. After certain rotation, the diffraction pattern changes, because some other plane will come perpendicular to the electron beam. The diffraction pattern basically depends on what are the planes which are perpendicular to the electron beam, and those planes will give diffraction, and that is how you get this pattern. So the moment you get a pattern like this, from this I can clearly say that this has to be a cubic crystal, because rhombohedron and hexagonal cannot have a 4-fold symmetry. So the moment I see this, I can find out that it is a cubic. So this is how one can find out. Yes.
So then how can we distinguish between rhombohedron and hexagonal?
Yes, we will come to that. We will come to that. So this is what it is as far as the cubic is concerned. So and from the crystallography we know what are the angles. What is the angle between the 100 plane and the 111 plane? This angle is known, 57.3 or so. And once we know these angles from the crystallography, I can tilt the sample by that particular angle and then get this 4-fold symmetry. And the moment if I don't get that 4-fold symmetry there, then it is clear, it is not cubic, it has to be one of the other 2. Isn't it? And so that's how one can find out. And if one wants to confirm that it is not really 3-fold, but it is 6-fold, there is a technique for that. It's called convergent beam electron diffraction. CBED people call it. Convergent beam electron diffraction is a technique which is nothing but an electron diffraction technique which is used in most of the conventional electron microscopes, transmission electron microscopes, where you can really see the information from the second layer of atoms, because when you converge the electron beam, the beam will be more intense, and when it falls on the sample, not only the information from the first layer of atoms, but from the second layer of atoms which are below that also you can find out, and from that one can get an idea whether really it is a 6-fold or a 3-fold. That's how one can get information, and this is how we can find out whether it is a real 3-fold or 6-fold. And that's how here we can see, though it looks 10-fold, you will come in a minute when we talk about the classification of quasicrystals. Quasicrystals have been classified into 3 groups basically. One is called one-dimensional quasicrystals. What are one-dimensional quasicrystals? One dimensional quasicrystals means those quasicrystals where in 2 dimensions the atomic arrangement is periodic. Atoms are periodically arranged in x and y directions, whereas in the z direction, in one of the direction, the atomic arrangement is not periodic, it is a quasi-periodic. It is not at the same time random, but it is quasi-periodic. We will come to this quasi-periodic in a minute. So this is what are called one dimensional quasicrystals. These are also called what are called vacancy ordered phases. That means in a crystal, if you can somehow make the vacancies in the crystal arranged in a certain order, you generate this kind of one dimensional quasicrystals, because vacancies are always arranged in a line like a dislocation. So these are what are called one dimensional quasicrystals. There are also 2 dimensional quasicrystals where the crystal or the sample or the solid has the periodicity in 1 dimension and quasi-periodicity in 2 dimensions. And the 3D quasicrystals are those where the quasi-periodicity is in all the 3 directions, which are called icosahedral phases. The 2-dimensional quasicrystals are called decagonal phases. There are examples for all of them. There are certain materials which possess only icosahedral kind of crystal structure. For example, aluminum manganese is one example. Aluminum copper iron crystals are such example, and there are examples for others too. So let's go back to this and have a look at this carefully. This is again a tenfold that we are looking at, and if you closely look at some of the diffraction spots, you can see the 5-fold symmetry really there. For example, here you look at this, the 5-fold symmetry is seen there. 1, 2, 3, 4, 5 atoms. They are not atoms, they are the diffracted spots, okay, but they give you some idea about atomic arrangement. And look at this, what is this kind of a symmetry? What symmetry is this? It is a 3-fold symmetry or whatever it is, okay. It is a 3-fold symmetry because icosahedron does not have a 6-fold symmetry, so it is only a 3-fold symmetry, okay. How do you know whether icosahedron has a 3-fold symmetry? You can see here, they are all equilateral triangles, so it has a 3-fold symmetry. So that is why we call it as M53 or 53M kind of crystal symmetry for a quasicrystal. And if you look at this carefully, what you see is in any direction you look at any one direction, one interesting thing that you see is that the spots are not equally spaced. You see, look at probably here also, let us say look at this direction in this 10-fold symmetry. Look at any one of this direction in one line, you can see this distance and this distance and this distance, if you look at it, they are not equally spaced, and that is a characteristic of a quasicrystal. In a crystal, any direction that you look at it, all the spots will be equally spaced because there is periodicity inside the crystal. Here there is no periodicity, it is a quasi-periodicity, and what is this quasi-periodicity? We will come to it in a minute. So this kind of diffraction patterns are possible, and in 1982 Shetman for the first time has observed that kind of a 10-fold, and this is the logbook of Shetman which he has written that day, which is April 8th 1982, where he has observed the 10-fold and he puts a question mark because that was the first time somebody is observing a 10-fold in a TEM. He was quite excited and then drew that particular diffraction pattern here, part of the diffraction pattern, and tried to take from each spot what is called a dark field and tried to look at that sample more carefully and found that it looks same from whichever spot that he chooses, and since then, but he took almost 2 years to publish this. 1983 in Physical Review Letters he published it. So he took 2 years to really confirm whether this is really 10-fold, and then repeated this experiment a number of, made a new alloy of the same composition and had a look at that, and then finally yes confirmed that yes, it is not an artifact in a TEM. It is not that TEM is misbehaving it, but it is a sample which is behaving that way. And then you can see this kind of images. This is nothing but a grain an aluminum copper iron quasicrystalline grain, which shows a clear, what kind of a solid is this? It is a dodecahedron, yes. So this is not a model, it is a grain in a material. It is an SEM picture of a sample in an aluminum copper iron. So this clearly tells you that the internal symmetry of a material is many times reflected from the outside geometry of material. That is why when people tried to look at sodium chloride crystals, that is when people started talking about the crystal structure. In fact, those days people have thought that external shape is same as that of the crystal structure. So that is why morphology, polymorphism, when the word came, morphology is nothing but the shape. So polymorphism is nothing but the different crystal structures. So the morphology and crystal structure, people used to use it very synonymously those days, because they know that in many cases this kind of thing happens, but not in all cases. You take an aluminum, all aluminum grains do not show you this kind of a thing, though it has an FCC structure. It is because of the constraints during growth. When aluminum grains are growing, the other grains are there around it which constrain from their growth. But if an aluminum individual grain is allowed to grow in an environment which is not constrained by anything else, it would definitely take this kind of a shape, and that is what is called, I mean not this exact shape, but whatever is the shape for the FCC crystal. This is what is called Gibbs shape of any crystal. If you have ever heard, every nucleus has certain shape. For simplicity, whenever we do calculations, we assume a spherical particle, spherical nucleus, but no nucleus is really spherical. Each nucleus has a particular shape which has been decided by the actual crystal structure of that material. Okay. This is the high resolution image from a quasicrystal. You can see these directions which are marked here, which clearly show you the atomic planes. Each dot, white dot that you are seeing is nothing but an atom, and the 5 directions indicating the 5-fold symmetry in that. And if you look at the basis of this quasicrystallography, what is quasi-periodicity? Quasi-periodicity is basically can be explained by what is called this Fibonacci sequence. What is a Fibonacci sequence? Fibonacci sequence is nothing but you start with one number 1, let us say, okay, and in principle you start with 0. Always keep adding the consecutive 2 numbers. That means add nth number plus n minus 1th number. If you keep on adding, you generate another number, and so you get a sequence. It is like a geometric sequence, excepting that you are adding the 2 consecutive numbers. So 1 plus 1, if you look at it, 1 plus 0, if there is 0 there, it would be 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13. So this is kind of sequence that you can generate. And if you look at the ratio of the successive terms, the first 2 terms are 1 by 1, then you have 2 by 1, then 3 by 2, 5 by 3, 8 by 5, 13 by 8, like that. If you keep on taking the ratio of the n plus 1 term by nth term, this ratio keeps on fluctuating and finally becomes, for example, first if you look at this ratio, first it is 1, then it goes to 2, that means it goes to 2, then it becomes 3 by 2, that means it comes to 1.5, then it goes to 5 by 3, 5 by 3 is how much? 1.66, so it goes up again, then it is 8 by 5 is 1.6, it comes down and keeps on fluctuating like this, and finally it becomes constant. And what is that constant value? That is what is called golden mean, which is equivalent to 1.618, which is called tau, and that is what is called the periodicity of a quasicrystal. So, the periodicity in a quasicrystal is given by this golden mean. That means there is always atoms arranged in a fashion in such a way that they repeat after some time. Instead of in a normal crystal you have a distance, let us say lattice parameter which we call, and this lattice parameter repeats. Here you may have an arrangement such as AB, ABC, and then that AB, ABC repeats, and again AB, ABC. If you define A as one distance x, B as another distance x dash, and C as some other distance. So, you can see that the atomic arrangement will be such that there will be a repetition. For example, if you look at the previous diffraction pattern here, I said the distances are not equal. This distance is different from this distance and this distance is different from this distance, but if you carefully take this distance, multiply this distance by golden mean, you will get this distance. The distance between the transmitted spot and the second spot will be equivalent to the distance between the transmitted spot and the first spot. Similarly, the distance between the transmitted spot and the second spot multiplied by the golden mean will be equivalent to the distance between the transmitted spot and the third spot, and so on and so forth. So, there is some kind of periodicity, not exactly equal, but there is a relation between the distances, and that relation is nothing but the quasi-periodicity, and that is what we call a quasi-periodicity. And this is different from completely randomness. It is not completely random, but at the same time it is not completely periodic. So, it is somewhere in between, and that is why we call them as quasi-periodic. This is observed from the crystal structures. A number of such crystals have already got this kind of an arrangement, and how you get it you will see if you take this kind of a thing. What you see is that you can also generate this kind of quasi periodic arrangement if you take a two-dimensional crystal and project it into one dimension. What you see here is a two-dimensional crystal. For example, these lines that you have, imagine them as atomic positions in a two dimension. So, you have a periodic arrangement of these lines in this direction and also in this direction. One can also do it in 3 dimensions, but it is more difficult, so we are showing it in 2 dimensions. So, if you take a 2-dimensional arrangement of atom and draw a line at a certain angle and draw another line which is parallel to the first line that you have drawn, that means 0 x dash. For that you draw another parallel line which is dotted line there, and choose all those points which fall into this domain. If you call that as a window, whatever atomic positions or lattice points which are falling into that domain, you choose them and then project them onto this x. If you choose, for example, within this domain, this falls, this falls, this falls, this one falls, this one, and this one, this one. There are so many which fall into that. All of them project them onto one line, which is this line, which is the horizontal line, x direction. If you project and now look at the distances between these projected spots.
Sir, what is the difference between those two lines?
That is just to have a choice. If you do not have a window, there will be innumerous number of atomic positions which have to be projected. Instead of projecting innumerous number, we define a certain number of atoms which can be projected, because if you project a large number of them, then you will have too many atoms, too many points projected onto it, all of them get clustered, so it becomes very difficult. So, as a result, we choose some window. This window can be of any choice. Okay, that is not important. What is important is this angle. Now, if this angle is having a certain finite value, if the tan theta is 1, then the projection, that means if the when is tan theta 1? If the theta is 45. So, if the theta is 45, then you choose all those parts which fall into this window or all those parts which intersect this particular line and project them. What you see is the distances between these projected spots will be equally spaced, and that is nothing but a crystal, isn't it? That is what is a periodic arrangement. So you can call it as a one-dimensional crystal. A two-dimensional crystal has been projected into a one-dimensional crystal now. Instead of this tan theta being 1, if this tan theta has certain finite values such as 1 by 2, 2 by 3 like that, then you get what are called rational approximates. I said certain crystal structures which have some similarity with quasicrystal, these are what are called rational approximates. So the distances between the projected spots will be such that they will not be periodic, but at the same time they will not be quasi-periodic also. And if this tan theta is tau 1.618, that is when you get a quasicrystal. So that's why nowadays people imagine a quasicrystal is nothing but a crystal in a higher dimension, and it has been projected into a lower dimension to give you a quasicrystal. So like this, if you can see, a two-dimensional crystal can be projected into a single dimension as a quasicrystalline arrangement of spots by choosing an appropriate angle, which is nothing but the tau, tan tau, okay, tan theta being equal to tau. Instead of that, if I take a 4-dimension, if at all there is a 4-dimensional solid that is existing, and project it into a 2-dimensional plane, what I get is a 2-dimensional quasicrystal if I choose the angle appropriately. And if one can extend it into a 6th dimension, there are thousands of people in this field who are doing what is called quasicrystallography, which is simply nothing but mathematics, where projection mathematics we call it. Okay, so where people take crystals, imagine what would have been if it in 6 dimensions, and if each of these 2 dimensions project it, you get a 1-dimensional quasicrystal. And if you take a 6-dimensional cube, if there is a 6-dimensional cube, and if that is projected, what you end up is in a 3-dimensional icosahedral quasicrystal. This is just mathematics, but just to understand what is the relation between quasicrystal into a crystal, because we know crystals, but we do not really know quasicrystals. How to understand quasicrystals in terms of crystals? And if you want to look at what are the, for example, if you look at this icosahedron, how many vertices, how many axes are required to define icosahedral quasicrystal? For example, if a solid has a quasicrystalline structure, a normal cubic structure, when I am talking of various planes, I talk of HKL, 3 indices. If I go to a hexagonal, I go into 4 indices. If I talk in terms of quasicrystal, I have to have 6 indices system. 5 indices for each of these pentagonal corners, 1 for the C axis. But in principle, one can convert these 6 indices into 3 indices, like the way we convert the 4 indices in a hexagonal to 3 indices system. So one can convert these things, and that's how people talk in terms of the quasicrystallography. And one can take this kind of tiles and tile them together with various rules and get a 5-fold symmetries. These are what are called Penrose tilings, and number of people are working on such tilings, which is all mathematics. And now finally we can come to the definition of a crystal, which has been modified in 1991, where they say any crystal having an essentially discrete diffraction pattern is a crystal, just to include a quasicrystal, because all quasicrystals give you a discrete diffraction pattern, and that's how we define a crystal. With this we stop and continue in the next class. Thank you.